Here is our exclusive logical gate XOR, and these are our inputs. This is a graph based on our inputs, which are X and Y. As we can see on this graph, we cannot separate them with only one line. They are not separable with one line. There is no way to do that. So we are required to use two different lines. And we also learn in our artificial neuron that each line with its equation is representing one neuron. So how can we show it with a artificial neuron if we have two lines? In order to do that, let's just transfer them first on their OR and environment. Here I'm just transferring them. We just took an and OR of them, and this is how they look like. Now they are trackable, they are separatable, and we can already separate them with one line. And this line, we can write an equation for it. Let's say if this is Z2, we can show this is Z1 plus, here is just passing from, let's say if this is 1, then it would be 0.5. Z1 plus 0.5. Meaning we can write an equation for that and we can represent it with one neuron. So let's take a look at this block over there. These are our inputs. The thing which we did here was first take the and OR of them. In previous sessions, we already saw what are the equations for and OR and how can we show them with a simple neuron. Now we are moving to another layer. This layer is our N3. Z1, here we have two lines, Z1 and Z2. Z1 is X and Y, Z2 is X or Y. And finally, we will have a Z3. We can show that this Z3 is equal to X or Y. Or simply, we can already write it as, let's say, transfer all of them in one side. Z2 minus Z1 plus 0.5. With this XOR gate, we solve the problem and we also provide a solution, a practical solution for it. This is a simple example of multi-layer perceptron, which we know it as MLP. We had this structure and we were able to classify this structure by making it into different layers. This is the basic fundamentals for multi-layer perceptron.